All right, so let's label, let's literally say that all these resistors are the same thing. I don't know, let's call it 10 ohms. And let's say that little r is 0.5 ohms. Let's say that V is 10 volts, and the EMF for that battery is 15 volts. No guarantees that the numbers work out here, work out friendly like they probably won't. And we'll probably need it later, but let's call this one number 1, and number 2, and number 3. So first step, equivalent resistance, yeah. So I would redraw this. I don't know if I would. Yeah, I guess I would redraw it. So I would say that it's kind of like that. I'll leave this. Well, this part has an equivalent resistance of 5. So I'm going to leave that one in there. I'll even leave this one in there. And we'll call that one a 5 ohm. And here's another 5 ohm. And here's our 0.5 ohm. Maybe I'll redraw that because I can redraw these two batteries together. Why is it 0.5? Because I did. Well, I don't know why I put 5 there. It's 10. So let's see. These batteries, let's see. We have, well, this is high to low. We've lost 10. But here's low to high up to 15. So I'd say that's just like a low to high this way of what? 5. Now let's combine all these resistors into one, and what do we get? 15.5 ohms. Numbers will really not work out nicely, but that's okay. So if I do I total, V total over R total, recommend the use of a calculator. What? 0.3? Yeah. Let's call it 0.32. Okay? And then work backwards. So I would say that V here is IR, or 1.61. And V here is IR, or 3.2. And there's a drop across this internal resistance of 0.16. And gee, I hope we've done that right. How could we tell? Add them up. So 1.6 and 3.2 is 4.8. But rounded down a little bit. Here's 4.9. Yep, that 4.96. That's close enough to 5 to account for rounding. Good. And well, let's see. Then we could find the current. Well, the currents if there's 0.32 amps that comes that way, how much of it goes in each direction? Half each way, because they're the same resistance. That's the only reason why it's the same each way. If they weren't the same, I would use this and say that's the potential difference across each of these R's. And then you'd know V and R, you could find I. Those I's would have to add up to the total. Okay? The potential difference across that battery, which we refer to as VPD, you know how to do that? Yeah, it's just E minus I little r. We were just saying there's a gain across the battery and then a drop across the little resistor. It should leave us with an overall gain. So that's 15 volts minus 0.32 times 0.5, whoops, amps. And we said there's that drop, 0.16. Woo! So that looks like 14.84 volts. Okay? I wish I made the, well, if we go the potential difference from point A to point B, yeah, I mean, I would just say, we said that current actually goes this way. So if we start here and, well, go, for example, like that, there's only one drop that we encounter. All right, if we go in the direction that conventional current actually flows, we say there's a loss in potential there. So it would just be I times R, or 0.32 times 10. No, not true. Sorry, not 0.32, because not all that current goes through there. 0.16 times 10. So we would say that V at A is, whoops, V at B, no, plus 1.6 volts, right? Potential at A is higher. But if I like put point, C like right there after that battery, we would have dropped 1.6 here, and then dropped another, right, high to low, so dropped another 10 volts, we'd be down 11.6. All right, and then drop here another, well, that's a whole 3.2, so that's 14.8, but then we gain 15, low to high, that gives us up to positive 0.2, but then we dropped the 0.16 or 0.2 there, we're back to nothing, right? In a whole loop, we'll have a net gain or drop in potential of 0. So says Mr. Kirchhoff. Okay? All right, folks. Tomorrow, the hammer, drop it. I'm kidding. It won't be that bad. I mean, no. Yeah, no.